will create chips that enable to study the origin and consequences of ciliopathies. So we welcome you, Dr. Tanveer sir, to our
Thank you.
program on micro-electromechanical system. Thank you.
All right, thanks. Thank you for the introduction. Let me try to share my presentation.
Thank you.
And yeah, because this is first time I'm using Google Meet, so you can just let me know if quickly how to share it.
Yeah, Tanveer, there are 3 dots at the
Yep.
right, on the right bottom corner. Present now is there. Besides that, present now is, you will find present now. At the bottom strip, you will find for present now.
Okay, yeah.
Have you got it?
Yes.
Yeah. You go to your entire screen.
Okay, fine. Yeah, I got it. Okay, I got it.
Yeah.
Thanks. Okay, yeah, it's uploading. Just a minute.
Yes, it is presenting. Yeah, your screen is visible.
Okay, so this is the full screen visible to you, right?
Yes, it is full screen visible. You can proceed.
Okay, fine. Well, welcome to this session. I'm gonna talk about femtosecond laser machining process. So, as was said in the introduction, I work on the cilia fabrication. So I'm gonna talk about the cilia structures first, and then I will talk the basics of the femtosecond laser machining process. And then we will see how we are trying to use this process to fabricate these structures. So the outline of the presentation will be cilia and their different shapes and forms. So we'll see how and where they are present in our body. And then I'm going to talk the basics of the femtosecond laser machining process. We will see there how this process is being used and how this is different from the other process that we use for fabricating microstructures. And the microstructure fabrication third session is actually the cilia fabrication that I will talk a bit about. So cilia is an organelle. It's present on the cells, the biological cells. And as you can see, there are multiple organelles in a body. Well, before I go into this, it's a bit of a bio perspective. And I know from the background of the participants that many of you are from the mechanical and electrical engineering. So I'm going to talk about the basics of the cilia as they are present in the nature. So this is simple introduction to where and how they are present in nature. So as you can see, the cell has different organelles and the nuclei, mitochondria, and other things. And you see this hair-like structure sticking out of the main body of the cell. And this is what we call cilium, a single structure, and a multiple structures called cilia. So they're present in our body almost everywhere. They do a lot of different functions in our body. For example, the main examples I have shown here are the ones on the right side, the second one. They're present in the kidneys, and there they act as sensors. So they sense flow and all inside the kidney. And also up here, you can see they're also present in the brain cells. So this image here is shown the cilia present in a mice brain. And they serve different functions. And they are present in a large number inside our windpipe, the inner lining of the trachea. And they help in clearing the mucus. And when we inhale, for example, a lot of dust and other foreign particles that go inside. So the cilia produce motion that allow the mucus with the foreign bodies stuck in the mucus to filter them out of the body. And down here, you will see the cilia. They're also present in the female reproductive organs, for example, the fallopian tube, where they help to move the egg from one to another point inside the reproductive system. So these are the main examples. However, they are present in a whole lot of other places in our body and in multiple organisms, I will say. So and serving a whole lot of different functions there. Now they they may be either primary cilium, which is that they do not move. For example, in that case, they may act as sensors, and they may act as other sensory organelle inside the cell, or they can produce motion. And when they produce a certain type of motion, they can induce flow or can propel cells and other things around them. For example, here, 3 typical motions that they produce is the corkscrew-like motion, which you see. For example, the flagellum of a sperm cell is a corkscrew-like motion. And then we have this asymmetric bending, which results into a wave-like motion called metacronial motion. And there also, this is the type of motion we find inside the inner lining of the trachea, where the cilia move, and then there is a mucus surrounding them, which then flows in one particular direction. For example, in case of trachea, it moves the mucus out of the body, and then that way the foreign particles trapped inside are filtered out. And there is a tilted conical motion. So in a tilted conical motion, which is more like a mechanical example, where you will say that when the cilia moves at a tilted angle, and when it is near to the floor, the viscous drag is more, so there is less effective force that is exerted on the floor. But when it comes up here in the vertical position, that time it can drag the fluid in a particular direction, and this way it can produce a unidirectional flow. Now, one particular example of this cilia that is present inside the embryonic node. So this is an interesting example, and I'm going to talk a bit about this. So what we see that during the early stages of the embryonic development, so after the fertilization, the embryo starts to grow, and after a few days, we see a tiny cavity is formed on the embryo and known as embryonic node. So what you see here in the first picture is a mice embryo after 7 days of fertilization. And in this small, what is shown here by a box, and then the zoomed up view, you will see that there are multiple these small hair-like structures in this tiny cavity. So the total width of this cavity is around 100 microns. And in that tiny cavity are these small hair-like structures. Now what they do, they undergo this tilted conical motion. And you can see in this video that this is how they undergo this tilted conical motion. And then you can see this particle here marked by the red circle. It moves in one particular direction. So what we know and what has been found is that that the direction of this flow, the direction of the fluid surrounding this cilia, the direction of the flow decides the orientation of the organs in our body later on when the embryo grows. So what has also been found is that if we can artificially reverse the direction of the flow in this tiny cavity, we see all the organs will be placed in the reverse configuration, like shown here. So, for example, there is a normal configuration of the organs in our body. The heart is on this side, liver on that side, stomach on that side. So this is the normal configuration. But we see during the early stages of the embryonic development, if the cilia do not produce this unidirectional motion, if the motion is in another direction, we see that all the organs in the body later on, when the embryo goes, the organs are placed in a reverse configuration. So the heart goes to the left, liver goes to the right, and other organs are equally placed in the reverse configuration. Now, there's a lot that's already known why this happens, and there's a lot to be known why exactly is this thing happening. And this is just one of the examples that how crucial is this tiny structure present in our body, and how big the effect could be because of this small motion that happens at the very early stage of the embryonic development. So this is one of the examples, but as I said, they are present almost everywhere in our body, and then they do a whole lot of other functions, and they act as sensors. They act as motion producers, and in this case particularly, they decide the orientation of the organs in our body and all. So they could be present in 2 different configurations. One is that they are normally present in our body, for example, and in that case they are just hair-like structures, but then they are present in different configurations. They could be like individual structures present here and there, or they are in a bunch making a carpet of these structures, and that way they are able to produce a motion, a whip-like motion, which actually propels the fluid. But in some other cases where we see that that the cilia may be defective, and in that case, you can see in the second image here that the cilia have developed a bulbous head, and this is a defective cilia. So as was said in the introduction, that I'm trying to study that what will be the effect of these defective cilia in our body. Now why is this important for us as engineers? We see, like the example of embryonic node, we found that although it's a bioprocess, but if we artificially reverse the direction of flow, we see that the changes happen a lot in the rest of the process that follows from there. So now from a bioprocess, it becomes a fluid mechanics process, because it is simply the flow that is deciding whether the organs will be placed in the right configuration or not. So that way, that is one of the reasons, and then many other reasons, for example, how they produce motion by undergoing different types of motions, and how they exactly are able to propel fluid, what's the magnitude of the fluid flow, what is the velocity that they can propel the fluid with, what is the viscosity of the fluid, all these things. And this is an inspiration for us to try to mimic nature and produce devices which are going to work at micro scales, which helps us not only to mimic the processes existing in nature, but also to make new devices, microfluidic devices. So while trying to mimic these structures, it has also been found that we can make really efficient micro mixers and micro pumps using these small structures. However, the fabrication has always been a challenge, and we want to know how to fabricate this structure. Or I mean, there are many ways with which these structures could be fabricated, but sometimes the size is the real issue, and they are so small. If I can talk about the smallest cilia, it goes to as small as around 400 nanometer in diameter, these cilia. For example, the one shown in the embryonic node, the size of that structure goes down to around 400 nanometers in diameter, and the lengths of around 5 to 6 microns. So it's really challenging to fabricate these structures with such small dimensions. And we have been able to fabricate many structures so far. Like I said, a lot of work has already been done on these structures, and different ways of fabrication, maybe microstereolithography or photolithography, and other processes that allow us to fabricate these structures have been used. But then you can imagine, if we want to fabricate a structure like this, which is a defective cilia, there we will see that we have to make this complex shape at a very small scale. And that's not that easy to fabricate by using the process that we know. And even if we want to fabricate these structures, it will be quite challenging to achieve that scale, because the individual structure diameter will be around 400, 500 nanometers. So how to fabricate this? And one of the ways that we are trying to fabricate these structures is using the femtosecond laser machining process. So I'll just first talk about the basic, how the femtosecond laser machining process works. So for example, if we have a substrate that is shown here, we use gloss substrate. So I'm going to talk about why we use gloss substrate. I'm going to talk about what type of laser we use there, and I'm going to talk about how the gloss or the material could be modified using the femtosecond laser machining process. Now, imagine this is a gloss substrate. What we do is that we focus a laser beam somewhere in this surface or in the substrate, or maybe on the surface of the substrate. So what happens at the focal point, we see the material gets modified in a certain way. We will see how that gets modified. And when that happens, what we can do next is that we can scan this laser beam from point A to point B. So while the scanning is happening, we see that the material gets modified all along the way where the laser beam has scanned. And it doesn't remove the material, it just modifies the structure of the material at that particular point where the laser has hit the substrate. And after that, what we do, we put it in a chemical bath, and the part that is exposed to the laser is now easy to be dissolved in the chemical. So some changes happen which allow it to be dissolved very easily in a chemical bath, and we get this type of a cavity. Now this concept could be used to make whole lot of different types of structures. But again here, when we use this principle, then we need to see why is it important as compared to many other processes that already exist there. So the first thing there is that what is the minimum size of the affected zone. So if the minimum size is very small, that means we can really make really small structures using this process. And so the other important thing is how is it different from the other laser processes? There are many other ways of fabricating structures using different laser-based fabrication processes, or maybe, for example, ablation, like where you hit laser with high power and then the substrate gets ablated and all. So this is here to show the difference. Why is this process better than many other processes that we use based on the laser? So we can see here on the right side what's machined using a femtosecond laser, and on the left side is using a nanosecond laser. So there we see that that the finish, you can see in the left side that it has a lot of roughness, while on the right side it doesn't have any roughness. And the reason is that the laser, which is using femtosecond process, does not affect the material thermally. It doesn't have a thermal effect on the material, while the other processes, for example, the laser with a nanosecond pulse, they affect the material thermally. So they distort it, and that results in this roughness of the features. So this is the main advantage of using the femtosecond laser machining process. So next is the material. What material we use there for making the structures using this femtosecond laser. And the material we mostly use, or I will say always use, is the fused silica, which is just a pure form of glass. And the reason is that because the material is highly isotropic, and it's chemically stable. It is biocompatible, high durability. So it has all these properties: excellent optical properties, high failure strength. So the two important properties I will say is the excellent optical properties. So that way, what you can do is that we can take this laser beam and focus it somewhere in the middle of the glass substrate, or maybe on one surface, and then we can go down to the middle, to center, to any other position within the glass substrate. And that way we are able to modify this glass using the laser at different locations in Z direction. So we can that way fabricate, or we can that way modify the material in 3 dimensions. Like I said in the previous slide, that we take the laser beam and we scan it at different points along the substrate, and then wherever the laser hits, the focal point hits the substrate, it gets modified, and then that way we can dissolve that away into a chemical bath. And the other thing is the fused silica is highly stable, chemically stable. So when we use a chemical bath to dissolve the exposed part, the unexposed part remains unaffected. So almost nothing happens there. So this gives us an advantage to dissolve away one part and let the other part be there. So this is sort of a reverse of many other processes like 2-photon polymerization and all, where we take a fluid and solidify it, but here we take a solid substrate and we expose, we modify it, and then wash away that particular part exposed. So this is the femtosecond laser. The property of the femtosecond laser is that the most of the energy of the laser is concentrated within a very small time band, which is less than 1 picosecond. That's why it goes to the femtosecond zone. So this left side image shows that how these lasers are produced. We always have a constant wavelength in the lasers. However, the power keeps on changing over this over the length of the laser beam, and this amplitude variation is amplitude results in the variation of the energy that's present in that laser at that particular point. So if we plot an energy graph, we will see that these peaks, the peaks in energy, which are concentrated in a very small time band, like I said, less than 1 picosecond. Now, the energy is distributed at different points, but the wavelength always stays constant. What we can do with these parameters is that we can change these parameters. So we can have a pulse energy, uh, of different magnitudes, and that changes the average power. We can have a repetition rate of the pulses. So now thing to notes here is that we do not change the wavelength. So wavelength is always constant, but we only change the uh, pulse repetition rate. So we can increase or decrease the distance between the two pulses, and that way we can have the laser pulses hitting the target at different time intervals. So we can also change the pulse duration. Like I said, it's always less than 1 picosecond, but within that less than 1 picosecond, we can change its duration. So we are presently using this wavelength of 1030 nanometer, but in principle, we can have other wavelengths, other lasers of different wavelengths that we can use for the same process using this, their same femtosecond laser machining process. So now, like I said, that the laser is, because the glass is, it has a high optical property, and then it allows the laser to pass through it without absorbing it. But that happens when the laser is not focused. So this is the advantage that we are using for machining or modifying the glass. So when the laser is passed through the glass, it just simply gets transmitted through it. It is not absorbed. But when we focus it at a particular point, then for the glass, we see that if the energy at the focal point goes above 100 gigawatts per meter square, per mm square, then we see that the non-linear effects come into play, and then the electrons are smashed out of their orbits and the plasma generation happen, and which actually results into the modification. Now you can see, as I have shown in the second image, that the focal point could be somewhere in the middle of the glass substrate as well, and there the material gets modified deep inside the glass substrate, and from there we can now scan the laser beam and then modify the material accordingly out to the surface. And the other thing to be noticed here is that because we need to later on chemically etch this away or dissolve the part that's exposed, so we need to have an inlet. We need to have the laser wave modifying the glass substrate from inside all the way out to one of the surfaces, so that the etchant can later on go in and dissolve the parts. So this is what actually happens. It's quite a complex process. So when each pulse hits the substrate, it actually results in a whole lot of different processes in a very small time. Like I said, the absorption of photons initially happen, and the avalanche ionization, that is the electrons are smashed out of the orbit, and then they result in the smashing out of further more electrons, and this way a chain of this avalanche ionization happen. So you can see here, the important thing is this thermal diffusion. So when the pulse hits, apart from all other processes that take place in a very short time interval, the thermal diffusion, the heat generated, because I said that the process is very special. It doesn't allow generation of heat, or it doesn't allow the modification of the material thermally. So what happens, the heat generated by each pulse is dissipated in less than 1 microsecond. So what we need to do is the following thing. So this is how we plan the pulse or the repetition rates. That means that how early or how late the second pulse will hit the substrate. And in that case, like I have shown here in the left graph, so when a single pulse hits the target, you see the heat is generated, and then it takes some time for that heat to dissipate away. So in the previous slide, I showed that the heat generated by single pulse takes less than 1 microsecond to dissipate away. Now, if we hit the target in a way that each pulse hits the substrate after 1 microsecond, that means the heat generated by the earlier pulse is now already dissipated. So the second pulse that hits the target is going to contribute to some thermal energy, but that will again be dissipated by the time the third pulse hits. So this way we allow the diffusion of the heat in a way that it doesn't get accumulated, and that the material is not affected. However, we can change that. We can change the reputational rate. We can have closer these pulses, and that way the heat keeps on accumulating inside the material, and we can actually thermally that time modify the material. So I can show you this in the graph here or in the picture. So what happens here is that we keep on increasing the repetition rate, that is the number of pulses per second, and we see that the material initially, for example, here you will see that there is a very small area that is getting modified. So as we keep on increasing this repetition rate, we see that the more and more area is getting affected because of the extra energy that we pump into the substrate. So important thing here is this, for example, this red dot, which is 2 micron spot size. So like I said, that we have to see, apart from other processes that we use for fabricating microstructures, how is femtosecond process better, or what are the advantages of this one compared to the other one. So the size of the spot, the minimum size that we can modify using the laser is dependent on the wavelength of the laser we use. And like I said, we use 1030 nanometer laser. So the minimum spot size, so the minimum area that can be modified using this process is around the wavelength of the laser. It is generally more than that, but it can in principle go to the dimension of the wavelength of the laser. So you see here in this particular study, they have used the spot size of 2 microns, so a laser with 2 micron wavelength, let's say, or smaller than that, but the smallest area that could be affected is 2 microns. And then you can see with the spot size of 2 microns, we have a big area that is getting affected if we increase the repetition rate, keep on increasing the energy that's pumped into the substrate. So that is in one dimension. That is like the spot size is equivalent to the wavelength of the laser, but that is in just one direction. So if I go back to this slide, you can see here, I have shown that the spot size is in an elliptical shape. And there, when I say the minimum spot size is equivalent to the wavelength of the light or laser light we use, that means the thickness of the spot size will be around that dimension. However, the length of the spot size is much more than that. And it can go, for example, in one of the laser systems that I worked on, the spot size length was around 10 microns and the diameter around 1 micron. In another system, it is around 20 micron and the diameter of 3 microns. However, this is also dependent on the optics that we use along with the laser that is already there with the system. So if we keep on increasing the magnification of the objective that is used to focus the laser beam, we keep on decreasing the spot size, but it cannot go smaller than the wavelength of the laser light that we are using here. Now, the reason that why it's in the elliptical shape, the spot size, is because once the laser hits the target, then what happens, the plasma is generated, like I showed in one of the graphs, that different phenomena happen in a very short time interval. So once that plasma is generated, it further concentrates the light into itself, and that allows the distribution of energy more in the Z direction than in the XY direction. So apart from the objective lens that we use to focus the laser beam in a substrate, when the plasma is generated, that itself acts as another lens and further concentrating this energy in a very small and narrow area. So this way, we are able to go down to this size, which is near to the wavelength of the laser, but then we can have this effect on a larger area by either increasing the number of pulses or by scanning it to different areas of the substrate. So the material modification, like I said, what type of modification happen in the material when the laser hits the substrate. So this is all, when I'm talking about the material, it's fused silica every time. Right now, all the study, most of the study has been done on the fused silica. So in one type of modification, we can have continuous modification. In this way, the material gets modified uniformly in a way that is later on used as a waveguide. And then because it's now modified in a way that it allows the light to pass through it, and then it can direct the light. So this is used as a waveguide. If this type of modification is done in a material, this will act as a waveguide. However, what we are more concerned about, or what we more focus on, is the second type of modification known as nanogratings. Because when I said initially in the basic principle of how we use this process, we actually expose the material to the laser and then we later on dissolve it in a chemical bath. And that will happen most efficiently if the material is modified with the nanogratings, with the nanograting formation inside the material. So if this type of formation happens in a material, it's easy for that part to be later on dissolved in the chemical bath. So we have to tune the parameters, which we will come to. But the thing that happens here is with the nanogratings, you can see that this is sort of now divided into many layers. So three effects happen there. One thing is that the density increases, the refractive index increases, and also the stress increases there at that particular point. So, well, in a very limiting case, I will say if we expose too much material, it can result in microcracks, but that's the details of it. However, in general, when we have this type of modification happening in a material, then these three effects happen. Most importantly, this change in the structure of the material, and which results into increase in density and increase in stresses. And perhaps that is one of the reasons that we can easily then later on dissolve it. And the third type of modification is the voids, where the laser hits, its parameters are tuned in a way that it can directly create void, remove the material out. So that way we can actually also, we use the same laser for ablation as well by tuning the parameters with high power, like intensity and repetition rate. So, but we are mostly concentrating on the nanogratings, and that is the type of modification we use for making the structures that we are working with. So here it shows in the graph, like I said, three types of modifications. One is the continuous modification for the waveguides. Second one is the nanogratings that we use for later on chemically etch away that portion. And third one is the voids. So here you can see the pulse duration, the laser pulse duration, and the pulse energy that is associated with these types of modifications. So if we tune the laser parameters in a particular way, we can get one or the other type of modification. But again, we are working in the nanogratings zone. So the principle that how it works is that we expose the material and then we dissolve it away. However, we may not every time need to do this, that we do not need to completely expose everything that we want to dissolve away. For example, if I give you an example that I want to make a small hole inside the material. For example, I want to make a small hole inside the material, and that way I do not need to completely expose all this part to the laser. What I can do, I can just expose the boundaries around it, so that the boundaries around it are later on dissolved when you put in the chemical bath, and we have a hole because a tiny cylindrical shape structure will come out, and that way we already have a hole in the substrate. So we don't need to expose completely everything that we want to dissolve away. So this is one of the strategies that we adopt while we want to fabricate something in a fused silica, because there we do not need to expose everything. We just have to see what's the type of structure we want to fabricate, and then accordingly design our scanning path so that we get rid of the most of the material that we don't want there, and also let the rest of the material be there, while saving us time and not getting us into a lot of dissolving or exposure of the material to the laser. So it's a rough video, a small video to show how actually when the laser hits the substrate. So what you can see here, this tiny glass slide here is the fused silica, and the object is on the top. And when the laser hits, you will see the bright flash coming out of it, and that's where actually the modification is happening in the material. So I play this video, you can see this bright flash. So this is being scanned in one line. You can see we are trying to cut this into small pieces here. So as we scan the laser through, the material gets modified, and this way we are able to change the structure there, and later on we dissolve it in the chemical bath. Now, as you can imagine, now more like other 3D printing processes, microstereolithography and other processes, we also have to use the scanning, the layered scanning. So like I said, the minimum spot size, the minimum area that could be affected using this process is 3 microns, for example, in diameter, and or like equivalent to the wavelength of the laser we use, and the length of the spot is around 10-20 microns depending on the laser, again, as well as the optics used. So we take that spot size and then we scan it in different tracks so that we have finally all the material that is modified there in a way that when we put it in a chemical bath, that material gets either dissolved or gets detached from the rest of the substrate, and we have a final structure with us. So there are two ways with which we generate these scanning paths, scanning patterns. One is you can directly write a program which is read by the machine directly, or we use a software where we can have a solid structure or the solid model, and then around the solid model we can generate these scanning paths, and then we export that program to the machine, which then starts scanning the substrate following that particular track, and then that way we can have the structure fabricated. So what I'm going to show you next is, for example, back to the artificial cilia. So this was about the femtosecond laser machining process. Initially, I talked about the cilia, where they are, why are they important, what functions and other things they do inside our body, and we are trying to mimic them in shape, in size, in function, and because they have complex shapes as well, like I showed the one which are the defective cilia, and they have these bulbous heads. So how do we fabricate such structures at such small scale? So that is something we're attempting to do using this process, for example. And here I am showing as an example, if I want to make this cilia, let's take, because in the biosystems they are existent in different shapes and forms, like I said, and the one way is that they have these bulbous heads, which could be very close to each other or far from each other. So as a simple attempt to first fabricate the simplest shape out of the glass material, for example, these type of structures I want to fabricate inside the glass material, and then what we do, we generate a scanning path around it. So here you can see this is the glass substrate, for example, and then I have to remove all the material around it so that I only finally have this type of structure left inside the material, which could be later on used for other things to be studied, to mold and demold them. But the first step is to make these structures inside a glass substrate. And for that, we use this scanning pattern, like I said, two different ways. So here I have used the programming where I generate the scanning pattern of each layer. So the top view shows, for example, each structure here is the cilium that I want to fabricate, each circle here in this patch. And on the right side, you see different layers. So I'm scanning the material in layers, so that in each layer, I take into consideration what is the amount of material that has to be removed. So you can see I'm not exposing completely all the material. I'm just dividing it into small square or cubical chunks that will be later on etched away. That will get detached and be removed from the main substrate. So this way, when we do and expose the material, here you can see in this one, this is the image of the actual material that is exposed to the laser in a particular pattern, like I said, and I showed in the previous slide. The grid, the scanning pattern that we use, and then we put in the etching. So this is a good image in a way that you can see some of the material is already removed and some is still there. So you can see these small, tiny, these pin-like structures that are still there, and the rest of the material is slowly getting dissolved and getting washed away. And finally, we have the complete removal of all the extra material, and then only these structures. So if you look at the side view, you see that each structure here, now the diameter of this structure here is 7 microns, and the diameter of the head is around 10 microns. So using this process, using the laser, this femtosecond laser machining process, we have been able to, of course, fabricate it in one way, the complex shapes, that is the bulbous head and all. However, this is the first step, and then we continue on to mold and demold, and then use different materials, how we can actually actuate them. So what we want to do next, like I said earlier, that these structures are not just stationary structures. They move, they make a whole lot of complex motions, and then we want to mimic those motions as well. So this is the first step, for example, making these structures in one particular material, but then we want to make an active structure. And I will just show you one video. I think that will be almost the conclusion of the talk. And this is one of the videos where you see cilia, which are slightly bigger in size, and then they are moving. You see, they're undergoing a near tilted conical motion. So these are simple without difference in the shape of the head with respect to the stem. But this is the motion that I would, or we would like to achieve with these structures as well, the ones I showed here with these structures. And now how to do that is something which we are going to try to achieve in the coming time. But so far with the laser machining process, we can actually make these shapes in one particular material. So to sum up, I will say that we have these interesting structures with a whole lot of different functions, and they're really complex. A whole lot of things have already been studied about these structures, and a whole lot still needs to be studied and is yet to be done. And we see as we learn more and more about them, we feel the more could be learned about them. And in our attempt to artificially mimic them, to artificially fabricate such structures, we are using this process, one of the processes, although with other processes as well, but this is one of the processes that we are using. And I was more interested in talking about the femtosecond laser machining process, which is quite interesting, and I feel it has a lot of potential. And then while we have achieved some of the structures that we want to fabricate, but the next step is, of course, to see how we can change them or mold and demold them into materials that will later on be actuated as well. So the artificial structure I showed in the last slide, the video, are the cilia structures fabricated out of a polymer with magnetic particles inside. So we use the magnetic field there to move them in a particular manner. And the same thing is to be done with these structures now, which is the work that's going on. And let's see how we're going to achieve that one. And with that, I would like to thank all of you. And I think this is going to be the question answer section now.
Yeah, sir. Dr. Tanveer, we can have the question answers.
All right.
Yeah. So any questions from the audience? Any questions?
Sir,
Yes.
is it sir, excuse me.
Yeah,
Yes.
yeah. Please go ahead.
Yeah, is it mandatory to use only glass material for this particular femtographic process, machining process, or any other material can be used?
So nice, yeah. That's a good question. So like I mentioned, that when we want to fabricate something that has to have a three-dimensional shape, for example, and in that case, the laser has to penetrate through the material so that we can focus the laser spot or the focal point at different locations inside the material. And that way it has to be transparent to the material. And that's why the glass is used, because it's highly transparent. Along with that, it modifies the material in a certain way that could later on be etched in a chemical bath. So we right now, of course, can only use glass material for making these structures, but for other processes, like I said, the ablation, for example, we can use any material, almost any material that could be ablated, but that thing could be done only on the surface. So that's not something we can go deep inside the material and then start modifying it there. So for three-dimensional structure fabrication, right now, yes, it's only through silica glass.
There is one question.
Yeah,
In chat box, there is one question from Professor Haseen Sheikh. What will be the resolution of drive that will move the either laser or substrate for modifying material?
Yes, so depending on the resolution of the drive, you will get the accuracy of the structure you want to fabricate. But the ones that are presently being used are highly accurate, and we are able to, for example, fabricate or move the structures, 1 micron at a time. So they are pretty precise. 1 micron is the step size, but the resolution is smaller than that in nanometers. And on top of that, we have the system to be highly stable. There shouldn't be the effect of the vibrations, the ground vibrations and all. And that could either be achieved by setting the setup on an isolated table or on a vibration isolation table, or we can have a very heavy system, for example, which is dampening the ground vibrations and not letting that effect go into the material. So that way, well, the laser will always be there, but you have good high resolution stages, and that will result in better feature size or shape.
Like
and
optical
you have
workbench.
less feature resolution.
Okay.
Yes, there are
Yes.
some, Dr. Tanveer, there are some piezo-based drive, so which gives like very smaller step size, so maybe lesser than 1 micron or so. Can we use that in for these systems?
Yes, but then we had to see that what is the maximum stroke we can achieve there, because
Yeah. That is the limitation of piezo.
yeah. So we are still using the linear translational stages, which are highly precise, I would say. Now, because the spot size itself is around 1 micron or slightly more than 1 micron, so that way it may not make sense to have something which has resolution less than 1 micron, because anyway the spot size is itself 1 micron.
How about like using voice coil actuators then?
Yeah, we can. I mean, it's just up to us what system we want to use. The basic principle is same. Laser has this this property. It can modify glass. However way you want to scan, we can do that. But that will then determine the plus and minus of the system that we want to use to scan the laser.
Okay. Any other questions? Any other questions from participants?
Hello, sir.
Yeah.
Hello,
Yes.
sir. Is this process will it be if in reality if it is going to be implemented like for the
Yeah.
particular materials like silicon or the fused
Mm-hmm.
silica
Yeah.
for that this process will work, right? Is what will be its probable application in particular
Yes.
in particularly? Yes.
So right now, like I said, because we are using fused silica, so the application is we can make almost any type of the microfluidic devices or microstructures, and that way that is just because this has the application of the generating nanogratings and all. That way we can use the structures, but apart from that, the waveguides that we can make out of this, and that also is being used in different applications. And the third one is voids, where we can do the ablation of the material, and that also has an application in making different devices, electronic devices and all. I mean, this has been used a lot, and it's very useful in making all these devices, because you have the flexibility of making three-dimensional structures, and
Yeah.
and with good resolution.
Yeah. Yeah. Thank you. Thank you. Thank you.
Any other questions from audience? Okay, I think there are no more questions. Yeah, no more questions. So
All right.
I thanks Dr. Tanveer for nice presentation on the femtosecond laser-based machining process and the application in processing the and fabricating the cilia, and then further further putting it into the application. So nicely explain all these concepts. So I thanks once again Dr. Tanveer. And that's all for the today's session for the participants. So we will meet tomorrow at 9:30 sharp. Thank
Thanks
you.
for having me. Thanks so much, everyone.
Yeah, thank you. There will be feedback link in the chat box. You fill the feedback, and then we will meet tomorrow at 9:30 sharp in the morning. Rashik? Rashik, are you there?
Sir,
Yeah, put
yes,
the
sir.
feedback link in the chat box.
Sir, I have posted it, sir.
Yeah, thank you.
Yes, sir.
Participants, please give the feedback, and tomorrow's session in the morning is by Dr. Suhas Moite from College of Engineering, Pune. So please all attend the session, and be log in 10 minutes ahead of the session so as to avoid the last minute rush. Thank you very much.